Hey guys, what's up? This is the self-taught reasoner implementation in JAX. This is a continuation from last video where we went over the research paper, and this is just going to be a quick video kind of outlining my implementation. I will code along very minimally in this video just due to how delayed this was, but let's just jump into it. And if you guys recall, let's start off with what the actual paper was about. Let's remember what this was. If you came from the last video, if you want a deeper explanation, I'll put the link in the description and you guys can review that. But essentially, this paper introduces this fine-tuning approach, which is pretty accurately described in both this diagram and this algorithm right down here. It's very straightforward. It is in an effort to teach a model to reason better for complex logical and mathematical analytical answers. We use the model's own reasoning as we create it into its own training data set. And you see it here where we input a pre-trained LLM with a data set of questions and answers. And what we do is we prompt the model to reason and generate a step-by-step trace of how to reach that answer. Now, this is what they mean with this R. This is like the predicted rationalization along with the predicted answer. And then we do two things. Well, there are two options. Either the model gets the answer right or the model gets the answer wrong. And what we do is, if the model gets the answer right, we save this R, this rationalization, the actual reasoning of the model, we save it into its own data set. So then we have a data set of question, rationalization, and answer. And we train the model over that data set to just more efficiently be able to reason through and more accurately. Now, the other option is the model gets the answer wrong. What do we do in that instance? We can leave it there, and just only take the correct answers and the correct reasoning traces and then fine-tune the model off that. However, that's not making the best use of our resources and everything. And so what this paper, I believe, more importantly introduces is the concept of rationalization. And what they do is, if the model gets an answer wrong, they perform a second step of adding a specific hint to the model. What that means is, now we give the model the question and we also give it the correct answer. And what we do is prompt it to reverse engineer how you go from question to answer. And in that way, even if the model originally got that question wrong, it now generates and reverse engineers a reasoning trace for that answer. Boom, we save that into the data set again. So now we have this huge data set of question, reasoning, answer traces. All, by the way, the reasoning all generated by the model itself. And what we do with that is we fine-tune the original model on the correct solutions, and then we do this again and again and again. Not many steps, maybe 3 or 4 times, but what this has shown is this brings, in a very cheap or relatively cheap way, right? You don't have to create a reasoning data set. You use the model's own reasoning to create its own data set. And this results in good findings, especially with rationalization. I think this is the most important finding. I believe this is for GS, Common Sense QA. So again, any logical questions that actually require some kind of reasoning trace, any data set with that. Here you can see without rationalization, we get pretty high numbers, but let's pay attention to the iterations, right? We're starting to see peaks in for example, for 3-digit numbers, the addition of 3-digit numbers, we see the peak in accuracy come around, what would you say, iteration 14, 13, around there. That's without rationalization. So that's just accepting the correct answers that the model originally gets and using that reasoning. Now, if we don't ignore the wrong answers and we go straight to if we don't ignore the wrong answers and we use that reasoning, and use those answers to reverse engineer some reasoning, what we get is, let's look at the 3-digit numbers again. Literally by iteration 1, we're already getting the same increase that we get by iteration 14. And this is one of the earlier papers that utilized chain of thought reasoning or chain of thought prompting in a way to directly affect the weights of a model. And that's what we'll be building here. Now, this is the main file. This is all in a repository that I'll link in the description below, where we're going over multiple concepts and techniques that are related to alignment, post-training, and reasoning of LLMs. And now, this implementation is rather straightforward, right? I mean, I'm not exaggerating when I say that the implementation is literally this algorithm. Most of the harder work has to do with any engineering related concepts. So this is the main implementation, right? Where we have a model, we have a tokenizer, the parameters of the model. This is all in JAX, where we have to abstract what the model and the actual parameters are. In PyTorch, they're all baked together. We have a test data set. I told you not many iterations. When I talk about number of iterations here, we're talking about the amount of times we actually loop through the algorithm and use rationalization, true or not true. This is for ablation studies later on. Now, the data set that I wanted to train with was was grade school math 8K. These are 8,000 examples. And what this data set has is this question and answer pairing, right? So we have these rather simple logical expressions here, like sold clips to 48 of her friends in April and sold half of many in May, and then how many she sell together. Like, we know kind of what that means. 48 in April, said half as many in May, that's 24. See here in the data set how you reach that answer. And it's separated by these 4 hashtags, the question and the answer. This data set, they use it also in the original paper. Right here. And that's, 8,000 is a good enough data set for us to kind of test with, or, that's what I wanted to test with. And yeah, so the first thing we do is load that data set. Now, in the actual data file, there's a little bit more like cleaning of the data that we have to do, right? As I said, there's 4 hashtags. Low-key forgot the names of them for real. I'm gonna just say hashtags, right? 4 hashtags that kind of separate the question from the answer. And so we want to normalize that, or we want to take that out, and then we want to also normalize the answers. Some of the answers might be in, not in this case, right? These are straight numbers, but sometimes we might get, looking for a specific example, none is showing up, but sometimes what we might get is like a $sign, for example, if we're talking about money. Different things like that. In the case of that, just in case, I didn't want to go through the whole data set. Same thing with the thousands. I just kind of tried to fix that up, clean that up so the numbers would just be straight, what they are. And then we also separate the reasoning from the actual data set. Now, some of these data sets had reasoning. For example, this is a reasoning trace. Now, we want to prompt the model in this way, but we don't exactly want to use this reasoning trace. We want to use a model's own reasoning trace. And this is so that it could be more like generalizable into the future in different data sets. Otherwise, we'll just be using the same kind of reasoning that is required for this specific data set. So we want to separate that as well. We separate that here. And yeah, that's what we load in, that grade school math 8K. We also have a sampler. Now this is all for Gemma's, Google Gemma's open source API. See it more here in the model. Here, make sampler. It's just for inference, for the model to actually generate. I forgot to mention the model that I'll be using is Gemma 2, 2 billion parameters. And this is just the pre-trained version, right? No instruction tuning. What we mean by that is kind of what we're doing right now, no post-training. And here what we do is loop through, and I'll explain the actual logic of the loop. But again, this is probably one of the simpler implementations you can do yourself. It is straight up a copy and paste of the actual algorithm we're given. The algorithm was laid out cleanly for us. We didn't have to figure anything out really. But the way this fine-tuning method would work is I created this list of examples and rationale generation. Here we generate actual reasoning traces, right? So we get a prompt, right? We make a prompt. You see it here. We either make a prompt where we give the question, we give some few shot examples for the model, and then the actual question, or we give them the hint, right? The hint happens where we give them the question and then give them the answer and then tell them, given the answer, generate the proper reasoning that would reach this answer. Those are the two prompts you have to make. That's how the prompt engineering works in this instance. And so we generate some output for the first instance, right? This is before rationalization. We generate an output given that prompt, and then basically what we do is we parse the reasoning and the answer right here. And if the answer that the model predicted is equivalent to the ground truth answer, then we append to our examples, which is our new data set. What we append is this question, reasoning, answer tuple, right? But if it's wrong, then we have to check if we want to use rationalization. You definitely should. But this is just to run an experiment I wanted to run and see the actual differences between the three. When I say the three, I mean with rationalization, no rationalization, and then just like a base model, just out of curiosity. Now, if we are using rationalization, what we do is we create a new prompt, the rationalization prompt, and we gather that output. And then that reasoning, we append it to the examples. Now we fine-tune our original model with these new examples, like this new data set kind of that we straight up made, and we just create a sampler with that new updated model. And that's kind of this part right here where we fine-tune the model, and then we create this copy of the model. That's basically what we do right here. And then we just run an evaluation on the model after whatever number of iterations using the test data set and see how much it improved. But that is essentially the implementation. It's 40 lines of code straight up. And this is just a bunch of like harnessing stuff I did so that I could actually evaluate it and run some experiments. But straight up, I have this pseudocode right here, and it's the exact same thing. And it's basically 25, 30 lines of code implementing this algorithm. So I hope this solidified how the algorithm worked. Next week, we're going to go, or next video, we're going to go into PPO, which is an extension, a further extension of reinforce, which is what we worked on last week. And yeah, I hope you guys all enjoyed and got a good project out of this for fine-tuning a model. And again, I'm going to leave the repository in the description. You guys can run the experiments yourselves if I haven't done so by the time I upload this. And yeah, hope you guys enjoyed.